Hi everybody. Today I'm going to talk about resistor in series and parallel. Let's review whatever you have studied before. In general, by Ohm's law, V equal to IR, or the voltage equal to the current multiplied by resistance. So in your circuit, sometimes we want to see the total resistance or the net resistance. So we're going to talk about two resistors for the simplicity in the case of our series arrangement and also in parallel arrangement. So let's get started with the two resistors in series. When you connect two resistors in series, as in the picture here, your net resistance or your total resistance is going to be just R1 plus R2. So that means you're going to have a larger resistance of the system. For example, if you have R1 equal to 10 ohms and R2 equal to 20 ohms, you simply add them up. So 10 plus 20, that's going to equal to 30 ohms. So that's what you have known, about it before. But at this point, we're going to see by using Ohm's law how you end up with R total equal to R1 plus R2. So from the circuit diagram here, I have R1 and R2 connected in series and also connected to supply voltage V. And we start from by Ohm's law. You're going to have the current flowing through the circuit. Circuit I at this point is going to be flowing through resistor R1 and resistor R2. So they both have the same current. And the voltage drop across R1, that's going to be IR1. Same as the voltage drop across R2 is going to be IR2. So from KVL, you're going to have V equal to voltage drop across R1 plus the voltage drop across R2. Then you can write the equation down. V equal to V1 plus V2, where V1 equal to IR1 and V2 is equal to IR2. So you end up with V equal to RT, or total resistance. And that means your RT is going to be equal to R1 plus R2 for series arrangement. Now take a look at two resistors in parallel. You will do pretty much the same thing. From the circuit diagram, you have R1 and R2 connected in parallel. So at this point, from the previous circuit diagram or for two resistors connected in series, you know that one condition is that the current flowing through R1 and R2 are equal. But for resistor in parallel, you know that the voltage drop across R1 and the voltage drop across R2. They're all equal, not the current. And from this point, you can calculate for the current I1. That's going to be equal the voltage or the supply voltage divided by R1 same as R2. The current flowing through R2 is going to be equal to V divided by R2. So the total current in your circuit is going to be equal to I1 plus I2, sorry. And then I1 equal to V over R1 and I2 equal to V over R2. So your RT simply equal to 1 over R1 plus 1 over R2. Or you can write 1 over RT equal to 1 over R1 plus 1 over R2 for power arrangement that you're probably familiar with that already. For example, R1 equal to 10 ohms and R2 equal to 20 ohms. Then 1 over RT equal to 1 over 10 plus 1 over 20. So you have 20 divided by 200. Or your RT simply equal to 200 over 10 or 10 ohms. So let's take a look at general cases. For R1 equal to R2, you know that your total resistance going to be half of one resistance of that resistor. So that's how we have our total to be R over 2, or half of one resistance of the resistor. Okay, let's move to the next page. Let's see your sorry. But this one is R2. Now take a look at resistor is parallel. I summarize right here. When you have two resistors in parallel, for example, you have 100 ohms and 10 ohms connected in parallel, your total or your net resistance going to be the product of 110 divided by 100 plus 10. So that's give you 9.09 ohms. That means it's close to 10 ohms, or the smaller resistance. From this point, I just want to point out that when you have the larger resistance and lower resistance connected in parallel, the net resistance tends to be closer to the lower resistance. That's the fact. And you know that when we're talking about larger resistor, that means the big resistor, or you have a lower resistance, right? Don't get confused. And the smaller resistor, that means larger resistance. Just want to point this out. Make sure you're not confused. Now let's point out for some trick. As you know, if you have n resistors connected, they're all connected in parallel, and they all have the same resistance. You end up that the total resistance going to be the resistance of one resistor divided by number of resistor. For example, if you have 100 ohm resistor, 10 of them connected in parallel, you're going to end up with the total resistance going to be 100 divided by 10, or that's give you 10 ohms resistance. Okay? Now Just for simplicity of calculation, this is the other way to look at your net resistance. For example, if you have a 5 ohm resistor in parallel with 10 ohm resistors, okay? Basically you have only two resistors, 5 ohms and 10 ohms. Now you can take a look at 5 ohm resistor. It's actually can made from 10 ohm resistor, two of them in parallel. So basically, when you connect it to a 10 ohm resistor, you end up with 3 of 10 ohm resistor. So that means you have 3 10 ohm resistor connected in parallel. In that case, you can apply, your R total equal to resistance of one resistor divided by number of resistor. In this case, is 3, right? So you're going to end up with total resistance to be 10 ohms divided by 3, or 3.33 ohms. And if you do a straightforward calculation, you simply apply this equation 1 over RT equal to 1 over 5 ohms plus 1 over 10 ohms. And that's end up with RT equal to 3.3 ohms. It's the same thing, but this one is the shortcut. Okay, that's you have to improve your skills, the way to look at calculations. All right, let's move to conductance. Okay, for resistor in parallel, you have equation 1 over RT equal to 1 over R1 plus 1 over R2 plus blah 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 to 1 over Rn. That sometimes gives you a headache. So why don't we take a look at the ratio 1 over RT just to be G. G is the conductance. That's opposite of our resistance. They represent conductance by G and the unit of Siemens and or is, which is 1 over ohms. And instead of with 1 over ohms, we call unit of G as mho, which is like spelled backward, MHO, or mho, which is the unit of G. But most often they call the unit G as Siemens. So when you apply to RT total of resistor in parallel, you're going to end up with G1 or G total equal to G1 plus G2 plus G3 blah 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 plus Gn. So you have n resistors in parallel. So that's something about conductance. Now since you already have the current, you're familiar with the voltage, you're familiar with resistance. Now let's move forward. In this case, we're going to talk about power in resistor, which is represented by capital P and in the unit of watt. Actually, watt is the unit of joule, the unit of energy per second. And P equal to IV, or the unit of amp volt or watt. And you can use the relation power with the current and resistance, which is I square R, or the power with the relation of only voltage and resistance. That's V squared over R. Now take a look at some examples. Take a look at the circuit right here. You have a 15-volt supply voltage connected to 1 k ohms resistor. You know that the power dissipation or the power drop across the resistor is going to be V squared over R, since V is given and R is given. So you have P equal to 15 square divided by 1000 or 1 k ohms. You have 0.225 watts. That's less than 0.25. I pick up this number because it's that we're familiar with this number, 1 over 4 watts or quarter watts. So with the 15-volt power supply and 1 k ohms resistor, you see that this is the less than 0.25 or quarter watt, 1/4 watt. And that means that it's not possible to access the power rating of 1 over 4 watt resistor. And if you have a resistor with the resistance greater than 1 k, this term is even less than 0.225. So it's no way for you to exceed the rating watt of your resistor from manufacturer, whatever. So this you can apply when you work on the real circuit. Now let's take a look at another example. One seeder requires about 10 to the 10th watts of electric power at 110 volts. That means your electric appliance at your home, you need a 110 volt power supply. Voltage supply. And if you have 10 million people in that city, so the average power required for each people is going to be 10 to the 10 watts, or watts divided by number of people. So you end up with 1 kilowatts. And the power is supplied through a cable 1 foot in diameter. For in case you have a pure copper electric cable, 1 foot in diameter, and that electric wire have resistance equal to 0.05 microohms per foot. So that's the very low resistance. Then let's take a look at the power loss per foot in electric cable. Power loss is going to be I square R. But in this case, V is given, right? This is 110 volt, and you will be able to calculate resistance. This is your resistance of pure copper wire, 0.05 microohms per foot. So you end up with P loss equal to 110 square divided by 0.05, 10 to negative 6, or 2.24, 2.42, 10 to 11th watts per foot. And you also be able to calculate the length of cable that all the watts electric power is going to be gone or lost, in copper cable. So you can find the length equal to P total divided by P loss. And your P total is like 10 to 10th that start electric power, and your P loss, or you lost in the copper wires, equal to 2.42, 10 to 11. So you end up with the length of your copper cable is the 0.413 foot. Okay? So hopefully this gives you some pictures to see whatever info in your resistor. In this case, we're talking about how to calculate the net resistance for two resistors connected in series and in parallel. And we go get into deeper details later on in the next video. Okay, see you. Bye.